So today, now that we're used to dealing with component vectors or vectors in component form, I want to look at one operation of vectors. Okay, we've talked about addition of vectors and subtraction of vectors. We've defined what the opposite of a vector is. All right, and we've defined one type of multiplication already. We've defined multiplication when you have a scalar times a vector. And you simply multiply each component by that scalar. Alright? What we have here is a little different because it's not a scalar times a vector, it's actually a vector times a vector. And if you were studying vectors a little bit more in depth, you'd actually learn that there's two ways to multiply vectors together. One is the cross product that we're not going to look at. The other is the dot product, okay? Now, the interesting thing here is that the dot product does not give us a vector. So we're multiplying two vectors together, and as you can see here, if u is the vector u1, u2, and v is the vector v1, v2, then u dot v, that's how we would read that, u dot v is u1 v1 plus u2 v2. Now, u1, u2, v1, and v2 are all just numbers, right? Mm-hmm. So when I do the dot product, what is my answer going to be? A scalar or a vector?
Scalar.
It's going to be a scalar, all right? I'm just multiplying numbers together and adding them up. So I'm going to get a number, a scalar, at the end. Can someone put this formula into their own words here?
Isn't it kind of like the, what's it called, adding like...
Double
angle theorems?
Hang on, what'd you say?
The sum and difference
Isn't it?
formulas.
Yeah, it's kind of like the sum and difference formula, but it's not.
I guess you could kind of think of it that way. But just think of it in terms of the vector here. We have u1 v1 plus u2 v2. What are we doing?
You're just multiplying the first of the vectors plus multiply of the second.
Okay, you're multiplying those first components together, and then the second components, right? So multiply the horizontal components together, multiply the vertical components together, and then add those two products together. All right? So just to illustrate what we're doing here, I have 4 different sets of vectors. I used all 4 different types of notation just so we could have some practice with them. All right, so the horizontal components in this first one here, 3, 5, dot 6, negative 2. What are our horizontal components?
3 and 6.
All right, so we have 3 times 6 plus the vertical components are
5 times negative 2.
good, 5 times a negative 2. So we have 18 plus a negative 10, and we get the scalar 8. Okay? So that's not too hard, right? Okay. Now we have 3, 9, negative 8, negative 4. So it's going to be 3 times negative 8 plus 9 times the negative 4. So negative 24 minus 36 is a negative 60. Okay? When you're given IJ notation, notice here the parentheses are not like parentheses up here. The parentheses are just to hold the whole vector together. Okay? So you're not thinking that it's 6j dotted with a negative 7i only. It's the entire vector, 4i plus 6j, dotted with negative 7i plus j. All right? So what would we do here?
4 and 7.
Okay, 4 times negative 7.
Plus 6 plus 1. 6 times 1.
Good, plus 6 times 1. So negative 28 plus 6 is negative 22. Okay? And with our last one, which ones are the horizontal components?
One's on top.
Good, the ones on top, alright? So, -5 times 11 plus 6 times 12. -55 plus 72 is 17. Okay? So it's a pretty simple formula, and once you get the hang of it, you'll do them really fast. But we're going to look at a couple of things that we can do with these here in a sec. Rebecca, did you have a question?
No, sorry.
Okay. All right. Now, I want to look at some properties. All right. Anytime we have a new operation, we need to consider some properties of that operation. So let's look at some of these first of all. U, V, and W are all vectors. C is a scalar. Notice first of all that the dot product is commutative. The order does not matter. Okay? Secondly, there is a zero product rule here. If you have the zero vector, which remember is just 0, 0, and you dot it with any vector, then you're going to get 0 times A plus 0 times B, which is just 0, okay? Notice here, this 0, okay, this 0 here is the vector, the 0 vector, because it's bold. In the print here, it's hard to tell. This is just a regular 0, it's the number 0, okay? The next thing we have here is that we have the distributive property with a dot product, okay? Now check this out here. If I do vector v plus vector w, am I going to get a vector or a scalar?
Scalar.
When we do vector addition, we end up with a vector, okay? So now we're dotting the vector u with this vector that's the result, and we get a constant at the end. However, you can distribute this u with a dot product to both v and w. And then notice I'm doing a dot product here, which gives me a scalar, and a dot product here, which gives me a scalar. So I'm just adding two scalars. Okay? So you can either add the vectors and then do a dot product, or you could do two dot products and add the scalars. Alright, it's up to you, but that's our distributive property. Okay? The fourth one here is kind of an interesting one. Alright, and this is one that you might use a few times here. If you take something dotted with itself, you get the magnitude squared. Okay? Watch this. Alright? Let's say V is the vector AB. Okay? What's the magnitude of V? This is a formula we should know. Yeah, square root of A squared plus B squared. Pythagorean theorem used to find the magnitude of a vector. Okay? Now, what if I had AB dotted with AB? The horizontal components are A and A, so A times A is A squared,
Plus B squared.
and the vertical are B squared, so A squared plus B squared. If you square the magnitude up there, you get rid of the radical, and it's just A squared plus B squared. Alright, so that is the magnitude squared. Okay? So that is another property of the dot product. Okay? And then number 5, I put that this one is kind of like the associative property. The associative property, if you remember, was when we had addition or multiplication with real numbers, and you could group them differently. Like if we had, 3 plus 8 plus 2, we could add the 8 and 2 first to get a 10 and then add the 3. Okay? So you could group it differently. Same thing with multiplication. This is kind of like that because we're not dealing with the same operation. Notice where there are two operations. This is scalar multiplication. Okay? This is a dot product. Alright? This gives us a number, and then we're just multiplying it by another number. But what this property is telling us is that if you have this, you could find the dot product first and then multiply by the constant. That's what's shown first. Or you could multiply one of the vectors, and you could actually do either one, multiply one of those vectors by the constant first, and then do the dot product. Okay? So maybe one of those vectors has components that are fractions, and by multiplying by the c first, it'll make them integers. Do that first, and then it makes it easier to find your dot product. Okay? Or maybe you recognize that one of the vectors you have has like a common factor. If you factor that out, like let's say you had the vector 8, 12, and you recognize that, oh, 8 and 12 are both multiples of 4. I could write that as 4 times the vector 2, 3. Then you could find the dot product with the 2, 3 to keep your number smaller, and just multiply your answer by 4 at the end. Okay? That's another way you could use this property. Okay? So, a couple of examples here just to take a look at some of these. And before we do the examples themselves, I want you to think, because anytime you're doing a problem with vectors, you need to think about what your result is going to be. Alright, here on part A, we're doing u dot v, then we're multiplying that by vector w. Okay, so u dot v, does that give us a scalar or a vector? Scalar. Then when I multiply that by vector w, does that give us a scalar or a vector?
Vector.
That gives us a vector. So our final answer here ought to be a vector. Alright? So let's actually do that now. Okay? U dot v, first of all. How do we get u dot v?
U times v plus u times v.
Okay, so what numbers am I using here?
-1 times
Oh,
2 plus 3 times -4.
Alright, -1 times 2 plus 3 times a -4. Okay, so that's a -2 minus 12, which is a -14. Then I'm multiplying that by vector w. 1, -2. And we get our answer,
-14, 28.
-14, positive 28. Okay? Now, B is a good example of what we were just talking about. I have u dotted with 2v. Okay? I don't feel like multiplying by 2 and making my numbers bigger, so I'm actually going to pull the 2 out in front, and I'm going to do the u dot v first. Okay? Well, we already got u dot v, right? U dot v equaled -14. So 2 times -14 is a -28. Okay? See how you can use these properties to kind of help yourself out a little bit? You don't have to redo the same work. Okay? This was u dot v, and then this was u dot v times w.
If you're pulling the 2 out of u times 2v, don't you have to make it 1/2 u?
No, it's not 1/2 u. What we did up here, it was actually just like this. We had 2 times the v, So instead, I brought the 2 out in front.
But then isn't that 2u times 2v?
Well, hang on. You're thinking of it like it's a u plus 2v. If we factored a 2 out of that, we'd have to do a 1/2 u plus a v. Okay? It's not vector addition there, it's a dot product.
Yeah, okay.
So it's just like multiplication. When you're adding and stuff, you have to factor it out of both of them. Well, this is multiplication, so I'm simply rearranging. Alright? I'm just rearranging them and grouping them differently. Okay? Alright. How about this one? It says the dot product of u with itself, u dot u, equals 5. So what is the magnitude of u?
Isn't that just square root of 5?
Yeah, it'd be the square root of 5, because remember u dot u is the magnitude of u squared. So that is the square root of 5. Okay. Any questions? All right. Now, the number one application of the dot product is finding the angle between two vectors. Okay? Here's what we're looking at. All right, the angle between two vectors. Now, make sure we understand what we're talking about here. I'm going to blow this up a bit. We have vector u and v that are both starting at the same point. Okay, that's important. There's a couple of things that we can see here. First of all right, the angle that we're dealing with, we're always going to look at it as the angle between 0 and 180. When we say between, all right, technically there are two angles here. There's this exterior angle there, and there's the angle theta that you see. We're always going to find that angle between them that's less than 180. Unless they happen to be opposite, and then they'll be equal to 180. All right, but don't give an angle that's bigger than 180. Also, notice something that we haven't looked at yet. You see how when we start them from the same point, when you draw the arrow to vector v, if you start at u and you go to vector v like this, you get v minus u. Now that's something that we haven't looked at yet.
How does that work?
Okay, well let's actually look at it.
You just go v and then you go minus u from where v ends?
Yeah, you could do that. Here's u. If I went from the end of v the opposite direction on u, so there's a minus u, then there we have it. There's v minus u. It's the same thing that you get up there. Okay?
It's like v plus minus u.
Yeah, v plus a negative u, or plus the opposite of u. Yeah, so this vector ends up being identical to that. So that's something we hadn't really looked at. It's not related to what we're doing right here, but since it was in the diagram, I thought I'd point that out to you here. Because that can be useful sometimes. Alright, so let's look at the actual formula. For the angle between the two vectors, the cosine of theta equals the dot product over the product of the magnitudes. Okay? U dot v over the magnitude of u times the magnitude of v. Okay? If you just remember it as the dot product over the product of the magnitudes. Okay? That's the easy way to remember it. Now that's the cosine of theta, so we'll need to take the inverse cosine if we want to get the actual angle. But this is the formula that we can use. So notice here, we have u, which is the vector 4, 3, I've drawn there for you, and v is the vector 3, 5. Alright, so if I want to find the angle between those, I need to find three things first. The dot product and both of the magnitudes. Alright, so let's do that first, okay? U dot v, what does that equal?
4, 3 times 3, 5.
4 times 3 plus 3 times 5. Good.
27.
Yeah, good. 27. 12 plus 15 is 27. So now I know the cosine of theta is 27. Now, stop for a sec. I got a positive number for my dot product. Magnitudes are always positive, which means my cosine is positive. What do I know about theta already?
In the first or fourth.
Okay, and since we're always going to give an angle between 0 and 180,
We know it's the first.
we know we're going to have an acute angle. Alright? If your dot product is positive, you'll always end up with an acute angle. Okay?
And if it's negative, it'll always be in the second.
That's right. If it's negative, cosine's negative in the second quadrant, it's always going to be obtuse. Alright? Now, what's the magnitude of u?
That would be word of you.
It's,
So 16.
there we go. We know our triples, 3, 4, 5. Right? So, do you see that 3, 4, 5? Right triangle, Pythagorean triples. Okay? So 16 plus 9 is 25, square rooted is 5. The other one's not a triple, so we got to actually figure that one out. So v is the square root of what?
That's where 9 plus 25.
Good, 9 plus 25 is 34. Alright? And you can leave it as a radical. Alright? That's okay, because we're going to just plug this into our calculators and take the inverse cosine. Alright? So it's 27 over 5 root 34.
And then our cosine.
Good. What's our inverse cosine of 27 over 5 root 34? Be careful on your calculator that you put parentheses around the 5 root 34. Otherwise, it'll just divide the 27 by 5 and then multiply by the square root of 34. You don't want that. Okay? You should have your calculators doing this. Alright? Not just waiting for one person to do it. Alright, good. So we get 22.16, or since it's an angle, we'll do 22.2 degrees. Okay? So, and because we drew it to scale, remember I said you guys don't have to draw things perfectly to scale? But since we drew it pretty close to scale here, is that a reasonable answer? Yes. Okay. It looks acute. If you're drawing it properly, you should at least be able to tell if it's supposed to be acute or obtuse. And it's a pretty small angle, 22 degrees makes sense. Okay? Anyone not getting that? Or having trouble with the calculator work? Okay. So that's the main thing that we can do there. All right? Now, I mentioned that I'll ask that question in a second. We have this term orthogonal. Orthogonal. Vectors u and v are orthogonal if u dot v equals 0. Okay? So that's nice. We have a way to classify two vectors. But I wanted to ask you something here. How does this relate to the angle?
Well, we know that if it's equal to 0, either u or v will be equal to 0.
It's just the dot product.
No,
wouldn't the angle-
just the dot product is 0.
Wouldn't the angle
Oh,
be
it's
180?
on
8,
five.
comma 0, 0?
Why do you say that?
Well, because we'd be going two separate directions, so that things would cancel out and just be, it would just, whenever you add them together, you get 0. All these are-
Not quite.
Are
Not
the
quite.
angles the same?
Is it undefined?
No.
One of the values of each zero.
No. Think about the angle. How do we get the angle? What's the formula we just saw?
Formula
So
is,
the dot product would have to be 0, right?
So it would be
Yes.
times.
Oh wait, it's 0 over
Yeah.
the magnitude.
Yes. What equals 0 over the magnitude?
Cosine of theta.
Cosine of theta. So let's think about this. Cosine of theta equals 0 over the magnitudes. Okay? We don't care what that equals because 0 over anything equals 0. If any of those were the 0 vector where the magnitude was 0, then the whole thing wouldn't even make sense. So it would be undefined. But here, the cosine equals 0. Where does cosine equal 0?
90.
At 90 degrees.
So it'll be 90 degrees.
So 90 degrees is just a fancy name for, or actually it's a simple name for the fancy term orthogonal, okay? Orthogonal vectors meet at a 90-degree angle. We could describe them as perpendicular, okay? Or their directions are perpendicular to each other, okay? And the angle between them would be 90 degrees. Just to see this once here, notice these vectors don't look any special or anything, but when you do the dot product, 2 times 6 is 12, negative 3 times 4 is minus 12, 12 minus 12 is 0. Okay? So that's it.